Okay, 1.2, exploring absolute value. Okay, so this is a new function that we're going to be talking about this year. Absolute value function, f at x equals, and then this is a bar, and then there's like our variable x, and then another bar. So these two bars are denoting the absolute value, okay? So on a number line, what this function is, like this function describes the distance, f at x, of any number x from the origin. Okay, so essentially we have, for example, absolute value of either 3 or -3 is just 3. It's like, how many units away from the origin is this? So we're only talking about positive values. So for the function f at x equals the absolute value of x, here are a couple points. So there is 1, 0 located at the origin. Okay. So it's going to be here. And the graph is comprised of two linear functions. So the two linear functions are going to be -x. And what that means is, if you remember y equals mx plus b, if you think about it, it's y equals -x. So the slope is -1, and then the b is 0. So y-intercept 0, of course, if we have a function that goes through the origin, then we have both an x and a y-intercept at 0, 0. Okay, and then we have f at x equals x, which is the positive. Okay, so these two chunks make up the absolute value of x. Okay, so we have the -x, and that goes from -infinity, which is way over here, and that goes all the way to 0. So what we do is we generally don't include the 0 for this one, even though we could reverse those inequalities. And then for x is greater than 0, or greater than or equal to, so for all of these values up to infinity, we have a different function. And we're also going to look at this style of graph very soon. They're called piecewise functions. We're going to get to that in this unit. Okay. The graph is symmetric about the y-axis. So going down this y-axis, we have symmetry left and right. Okay, and then as x approaches large positive values, so over here, these like approaches infinity, y approaches also large positive values. So it's going up. We're going to talk about more end behaviors tomorrow. And as x approaches large negative values, so of course approaching this negative infinity, y approaches large positive values. Okay, so again, it's going up again. Okay, when we look at domain and range, we have a domain of XER and a range of YER such that y is greater than or equal to 0. Okay, so like, you know, we use the word start, but it doesn't really start there, but like the bottom number 0 and then the y values are increasing. Okay, and every input in an absolute value returns an output that is non-negative. So therefore, no matter what, it's positive. So I have the absolute value function here, and of course, again, this side is going to be the -x, and this side is going to be the x. Now, using the graph of the absolute value function, which is f at x equals absolute value of x, let's take the following. So, domain. We go to the left and the right forever. We have XER. Okay, range. Oh, let me put those in squiggly brackets just to keep the form. Okay, range, we quote unquote start at 0 and we go up forever. So it's YER such that y is greater than or equal to 0. If you're using interval notation, you can put 0 to infinity. Okay, the shape of the graph, we can say that there are two lines. We have one x-intercept at x equals 0 or you can quote it as 0, 0 as an ordered pair. There's no asymptotes. Okay, we increase from 0 to infinity, right? So whenever we're talking about intervals of increase and decrease, you can make a little note, quote, with like the x's. So all of these right here, intervals of increase is going to be from 0 to infinity. And because we read a graph from left to right, so if we're reading this, we're reading it to the right. So we're increasing. And then the increasing is quoting the y values. The y values are getting bigger. We're going up. And then intervals of decrease. I know that there's an arrow here looking like it goes up, but since we read a graph from left to right, just like how we read a book, we're actually reading to the right. So from negative infinity to 0, we actually have an interval of decrease. Okay, and as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches, again, positive infinity. All right, example 2. Using the equation for absolute value, state the value of each of the function, or each of the following. Okay, so the absolute value is 5. So if we want to put this equation in like the side of our paper, we're going to have this piecewise function. This is what it's called. There's going to be two pieces of it. There's going to be negative x if x is less than 0, and we're going to have x if x is greater than 0. Okay, and there's going to be commas there. So 5, what is the absolute value of 5? So as like a cheat, I'm going to tell you, if it's just a constant, we're just taking the positive of it. However, if they want us to actually use the equation for absolute value, I'm going to come down here and I'm going to locate where 5 is in the domain. Okay, super important to locate it in the domain. So 5 is definitely greater than 0, so we're going to be focusing on this equation. So if you actually think about it long ways, we're like, okay, well, what's f at 5? Well, let's go f at x equals x. So f at 5 is also going to equal 5, and then that's done. Because of the simplicity of this, I find it a little bit confusing. So let's try B. What's the absolute value of negative 6? Well, locating negative 6 in the domain of this piecewise function, we know that negative 6 is less than 0. So it's going to occur, like it's going to land here. Okay, so we have our function f at x equals negative x. And then we're going to have f at negative 6 is going to equal, so check this out. Bring down the negative sign, plug in the x. So f at negative 6 equals positive 6. Again, short form is whatever constant this is, take the positive of it. Okay, C, I'm going to simplify this. So the absolute value of negative 6 plus 4 is going to be the absolute value of negative 2. Okay, and we know if we sub in f at negative 2, we're going to yield 2. Okay, and then the last one, this, just read the BEDMAS. We're going to have 3 times, what is the absolute value of negative 2? So f at negative 2. Well, that's going to be 3 times 2, right? So the absolute value of negative 2 is the positive, which will give us 6. Okay, express each of the following intervals using absolute value notation. So let's talk about what intervals these are first. So x is less than -4. So we have -infinity to -4. That's where it would be on the number line. So we would have here open circle on a number line and going smaller and smaller all the way to like -infinity. Okay, and then the next one is x is greater than 4. So we would have 4 comma infinity, and our numbers would go from open circle at 4, because it's not like the big box brackets, it's not underlined like that. So just open bracket, so open circle, and it would go to infinity. So if we want to express this simpler as an absolute value, we would say the absolute value of x is greater than 4. So what this actually means is any number that we plug in here, which are any of these numbers that would satisfy these two inequalities, or any of these numbers would also satisfy these two inequalities. These are where x, like this is what x could equal, and then it would be greater than 4. Okay, let's see that again, but let's see it with like the underlined inequality. So x is less than or equal to -6. So if we had a number line and we had -6 marked off, let's mark off 6, we would have closed circle, and we would have, -infinity to -6. Okay, so we would have closed circle, and then we would go all the way to the left to -infinity. Okay, and then we have x is greater than or equal to 6. So we would include 6 and then extend to infinity. So all the way to infinity, and we would include 6. So again, a closed circle and go all the way up. Okay, remember, we can never actually reach infinity, so we have to use open brackets for those. Okay, so in this case, the absolute value of x, so if we take any x in this interval or any x in this interval, right? So wherever the x is defined, we are going to yield, like if we subbed it in absolute value, we would yield greater than 6. Okay, so graph the following on a number line. So this is a little bit easier. So when we're graphing the absolute value of x is less than 4, again, so I'm just going to think of all values of x that are less than 4. Okay, and then like plus the negatives, right? Plus the negatives. Okay, so if we're having like, what numbers can we sub in such that the absolute value of those are going to be less than 4? So we can sub in 0, 0 is less than 4. 1 is less than 4, 2 is less than 4, 3 is less than 4. Let's open circle on the 4. So anything in this range here is going to be less than 4. Now, if we take the absolute value of -1, it's 1, still less than 4. Absolute value of -2 is 2, still less than 4. Absolute value of 3, or sorry, -3, right? The absolute value of -3 is 3, less than 4. So we're going to go all the way until -4. And that is the solution with open circles at the end. Okay, and then we have what values can we sub in for x? So when is the absolute value of x greater than or equal to 3? So for this one, we're going to think of all values of x that are greater than 3, and then obviously plus the negatives. Okay, so if we sub in 0, absolute value of 0 is 0. That is not greater than 3, so that's not in it. Absolute value of 1 is 1. That's not in it. That's not in it. So we're actually going to start at 3, and anything bigger than 3 is going to be, obviously, the absolute value of those is going to be greater than 3. Now let's flip. Absolute value of -1 is 1. That's not greater than 3. Absolute value of -2 is 2. It's not greater than 3. So we're going to start this side at -3, and we're going to draw a line to the left. So that is the solution there.